In our today's lesson, I want us to go ahead to the other law of motion. In this topic, we'll be looking at the laws of motion, which we say there are 3. So we are going to look at Newton's second law of motion. The Newton's second law of motion. Newton's second law of motion. So by the end of this lesson, you should be in a position to state the Newton's second law of motion, and again you should also be in a position to state the relationship between force, mass and acceleration. So those are our objectives for this lesson, stating the Newton's second law of motion and also being in a position to tell the relationship that exists between force, mass and acceleration, between these or among those 3, force, mass and acceleration. So Newton's second law of motion, and here I want us to consider a body of mass m. Consider a body of mass m traveling at an initial velocity u, that is the initial velocity, the units meters per second. Consider a body of mass m traveling at an initial velocity u meters per second. Therefore, it means that the initial momentum for this body, we can write it as pi, I for the initial momentum I, therefore will be given by the mass of that body, mass m, multiplied by the velocity of the body, that is the initial velocity, the velocity of the body v. And therefore, we can come and say therefore that the initial velocity is given by mass multiplied by, sorry, here it is not v because we are talking of the initial velocity u. So our initial velocity, this is initial velocity u, so it is mass multiplied by the initial velocity u. So this will be the initial momentum. Initial momentum will be given by mass multiplied by the initial velocity u. Now let's say a force F. Before we move on, we can talk of a force. Let's have a force F acting on that body, for time, let's say for a time t seconds, for some time, that is t seconds, and therefore the velocity will therefore change. If a force acts on the body for a certain number of seconds, so the velocity will change. The velocity changes to, let's say, v meters per second. So if a force F acting on the if a force F acting on the body for time t seconds, the velocity therefore will change to, let's say, v meters per second. A force F acts on the body. We can talk of a force F acts on the body for the time t seconds, and therefore the velocity changes to v meters per second. And therefore, we are going now to have the final momentum after the force has acted on that body. So therefore, our final momentum, which we can write as Pf, final momentum, will therefore be equal to the mass of that body, mass m, multiplied by the velocity. Now the other velocity after it has been acted upon by this force. So we multiply by the final velocity, v. And therefore our final momentum Pf will therefore be equal to mass multiplied by the final velocity. So this will give us the final momentum. So we have our initial momentum here, we have our final momentum, and the initial momentum. So all these we are moving ahead so that we can be able to derive the Newton's second law of motion. And therefore, we can simply come and say therefore we can be able to calculate the rate of change in momentum. The rate of change in momentum, the rate of change in momentum simply means we'll take the change in momentum. When you hear of the word rate, meaning that there is dividing by the time. The change in momentum divided by the time that is taken. So the rate of change in momentum will therefore be equal to change in momentum, and our change in momentum is the final momentum minus the initial momentum. So we are going to have the final momentum minus the initial momentum divided by the time taken. So this will be the rate of change in momentum. So this will be our rate of change in momentum, which is the final momentum minus the initial momentum divided by the time that is taken. So in this case, we had seen that a force F acting on the body, not just a force, but if an unbalanced force, this should be unbalanced, unbalanced force F acting on the body, so the velocity is changing to this. And therefore we can say that if we have a small force being applied, a small force applied, a small causes a small change. It also causes a small change in velocity. And because we said that velocity is directly proportional to the momentum, it therefore means that a small force causing a small change in velocity, it also means that this will be a small momentum. And again, a big force or a bigger force causes a bigger or a big change in velocity, and therefore this will be a bigger or a big momentum. And therefore we can see keenly that the force is directly proportional to the momentum, whereby if you apply a small force, it is causing a small change in momentum. If we have a bigger force, it will cause a bigger change in momentum. And therefore we can simply come and say, because force is therefore directly proportional to the change in momentum, so we can simply come and say that therefore the force is directly proportional to the rate of change in momentum. And therefore we can simply come and say therefore that force is directly proportional to the rate of change in momentum. Whereby this represents the change in momentum per time, so it is the rate of change in momentum. So when we have this relationship where force is directly proportional to the rate of change in momentum, this is simply what we are referring to as the Newton's second law of motion. And I want us to state the Newton's second law of motion. So we can say therefore that the Newton's second law of motion states that the rate of change in momentum is directly proportional to the external force producing the change and takes place in the direction of force. So the rate of change is momentum. The rate of change momentum of a body is directly proportional to the external force, is directly proportional to the external force producing the change place and takes place in the direction of force, and takes place in the direction of force. And this is simply what we refer to as the Newton's second law of motion, whereby we are saying that the force will be directly proportional to the rate of change in momentum. So therefore the rate of change in momentum of a body is directly proportional to the external force producing the change, and it takes place in the direction of the force. That is, in the direction of the force applied. And that's what we refer to as the Newton's second law of motion. So you can see where we are deriving the Newton's second law of motion, whereby first we are considering a body with an initial velocity u, so we calculate the initial momentum. Then when an unbalanced force F is applied on that body for a time t seconds and the velocity changes to v meters per second, therefore we'll have the final momentum, which will be mass multiplied by the final velocity. We can move ahead and calculate, because we have the force acting for a certain number of seconds. When we calculate the rate of change in momentum, it simply refers to the change in momentum all over the time taken. So we have the final momentum, subtract the initial momentum divided by the time taken. And we are continuing to say that when a small force is applied, it will cause a small change in velocity. And therefore, because momentum and velocity are directly proportional, so when there is a small change in velocity, there is also a small change in momentum. Again, a bigger force causes a bigger change in velocity, and therefore also a big change in momentum. And therefore we are saying that force is directly proportional to the rate of change in momentum. And this is what we are calling our Newton's second law of motion. And this is change in momentum. This is, when we have this is change in momentum, which is being given by the final momentum minus the initial momentum. That is the change in momentum. So Newton's second law of motion states that the rate of change in momentum of a body is directly proportional to the external force producing the change and takes place in the direction of force.